When you shake the free end of a rope up and down, the motion of the rope is at right angles to the direction the wave travels. Whenever the motion in the medium is at right angles to the direction of travel, the wave is a transverse wave. Some examples of transverse waves are a guitar string vibrating after being plucked, electromagnetic waves, which make up radio waves and light. Not all waves are transverse. When the motion of the medium is parallel to the direction of travel, the wave is a longitudinal wave. Sound is an example of a longitudinal wave. Some waves are more complicated. Ocean waves have both perpendicular and parallel motion, a kind of rolling motion. Earthquakes produce both transverse and longitudinal waves. Scientists use the properties of these waves to study the Earth's interior. Interference patterns occur when waves from different sources arrive at the same point at the same time. Objects can't share their space with other objects, but more than one wave can exist in the same space at the same time. If you drop two rocks in the water, the waves produced by each one can overlap and form an interference pattern. An interference pattern is a regular arrangement of places where wave effects are increased, decreased, or neutralized. Constructive interference is when the crest of one wave overlaps the crest of another and their individual effects add together. The result is a wave of larger amplitude called reinforcement. Destructive interference is when the crest of one wave and the trough of another overlap and their individual effects are reduced. The result is a wave of lower or no amplitude called cancellation. You can see an interference pattern in water. There are regions of destructive interference where crests and troughs overlap and have zero amplitude. We say the waves are out of phase. In the regions of constructive interference where crests and crests overlap, the waves have large amplitude. We say the waves here are in phase. Interference is a characteristic of all waves, whether they're water waves, sound waves, or light waves. If you make a wave by shaking a rope that's tight on one end, the wave reflects back to you. By shaking the rope at just the right frequency, you can cause the outgoing wave and the incoming wave to form a standing wave. A standing wave is a wave that appears to stay in one place. It doesn't seem to move through the medium. Of course, this is an illusion. Individual waves are moving through the medium, but the areas of constructive and destructive interference are not. Nodes are stationary points of the standing wave where there is total cancellation of the wave and zero amplitude. You could touch the nodes on a string with standing waves and you would not disrupt the wave. The positions with the largest amplitude are called antinodes and occur halfway between nodes. You can produce different standing waves by shaking the rope at different frequencies. Once you find a frequency that produces a standing wave, doubling or tripling the frequency will also produce standing waves. The higher the frequency, the more nodes and antinodes are produced. This standing wave has a 1/2 wavelength. If you shake with twice the frequency, you produce a 1 wavelength standing wave. If you shake at triple the frequency, you produce a 1.5 wavelength standing wave. Standing waves are set up in stringed musical instruments. Standing waves are also found in the air of wind and brass instruments, or in a soda bottle when you blow over the top.